Hey again, guys. I hope you all had a great Thanksgiving. As a result of mine, I've put away all my firework materials to free up some space. So this gave me some of the opportunity I needed to do this on-paper design video I've had in the works for a while. This particular video is about multi-break shells. I think this will give you a better understanding of how canister shells work and how to design them, rather than simply watching me make one particular sort in steps. I hope you guys can enjoy this video despite it being a little more taking a little more intelligence to figure out. It's going to take a lot of thought to really put everything together, but if you can chew through it, I think you'll find that your understanding of fireworks will greatly improve. So, good luck.
Double boom.
Alright, so as you can see here, I have a drawing of a multi-break shell. This is the design of the shell you just saw in the intro video, and one of the very first I ever made. An experienced shell builder would notice many flaws in this design, but at its core, it is about as simple as a multi-break shell can get. So regardless of the improper construction, I think it is worth explaining just to get the concept down.
Alright, getting right into it. As you can see plainly, this is a 2-break shell. Each break made very similarly to how I show a canister shell is made in my old videos, how to build a 1.5 by 3 inch can shell, parts 1 and 2. They are held together by vertical spiking, which I do not show in this drawing. You can see that these shells are shorter than a standard shell would be, which is done for stability, since taller shells undergo larger forces wanting to tear them apart after launch. You should be able to tell that these shells are fused together with standard visco, and that the bottom shell's fuse is ignited directly by the lift powder, which is shown here. The second shell's fuse is not ignited until the first shell breaks, which provides delay between each shell burst. The first fuse here is glued obviously into the first shell. The second fuse is glued only into the second shell, so that when the first shell breaks, the fuse is left securely in place. This fuse is inserted into the first shell in the construction process with no adhesive whatsoever, to allow the second shell to cleanly fall away after the first break. Finally, the quick match is run down the side of the shell and the lift bag is added. The last thing I would like to show you in this drawing is something that will come into play in the next shell design I am about to show, and that is the organization of the stars. You can see in this drawing there is a core of black powder surrounded by a ring of stars. This is not necessary for the function of a multi-break shell, but it is absolutely necessary if you want a good ring-shaped break. This ring of stars is achieved by wrapping a dowel in tissue paper and inserting it in the center of the shell. Stars are then packed all around it as tightly as possible. When the shell is full, the dowel is removed, carefully leaving behind the tissue paper. Black powder or black powder-coated rice hulls are then poured in the now empty core. Canister shells rely on the contents for much of their stability, so it is crucial that the stars and black powder fill the entire shell with no extra room. To ensure a snug fit for the contents, I use tissue paper above and below the contents to provide compression, as shown here. Okay, now here's the real shell. Many things are done similarly in this shell as in the last. As you can see, the stars are still organized around a core of black powder, which is formed in the same way with a dowel and tissue paper. The shell stability is also still reliant on the contents of the shell, which can still be compressed with tissue paper, though I do not show it in this drawing. The proper placement of the tissue paper would be right above the stars in the break, and would be added just prior to securing the top cap. Getting these shells down is crucial to moving on to multi-break shells, so pay good attention. If you perfect these, you will have an easy time moving on to simple 2-break shells, and then from there more complex multi-breaks containing many more shells. Alright, the first thing you should notice is that the shell appears upside down compared to the last. When you start getting into larger canister shells such as this, the shells are always fused from the top. Canister shells are always weakest on the fused end, so this is protection from the lift. In this cross section you can see the shell is made up of several layers. This shell demonstrates how a shell would be made from factory casings such as those from PyroDirect. Starting from the inside, the first layer is the factory casing and caps, and directly outside of that the spiking is applied. Hopefully you can see on the bottom of the shell that there are several discs. These are made of cardboard or another hard material and are held on by the spiking. The discs provide extra protection from the lift. More discs are needed the larger or heavier the shell becomes. In a multi-break shell such as what this video is progressing towards, it could take an inch or more of discs to keep the shells safe. The final layer is several layers of gummed tape, which are applied directly over the spiking and do a very nice job of securing the strands. With the addition of the gummed tape to the spiking, the wall of the shell gains a fiberglass-like quality and can withstand significantly more pressure. Now getting back to the fusing, quick match is run from the lift up the side of the shell, and a section of the wall of the pipe is cut away where it will contact the time fuse. The quick match is held to the time fuse with string or tape, the bare black match or PyroDirect fast fuse in contact with the exposed core of the time fuse. For the best chance of ignition, the time fuse is split with a razor blade, and a few strands of black match are tied into the cut in a process called cross-matching. I demonstrate how to do this in my video 3-inch ball shell construction. The entire setup of running quick match between fuse and the lift is called a pass fire, and is how all multi-break canister shells are fused. Okay, now I am at the point in the video where we are no longer worried about the contents of a shell, and I will simply trust that any shell used in this part is properly designed as shown earlier. The only thing that changes somewhat internally between a standard canister shell and the breaks of a multi-break shell is the fuse used for timing. You can see in this drawing that between each shell is a tube. This is called a spolet. It is a type of fuse made by ramming black powder into a tube. The amount of black powder used determines how long the spolet will take to burn to the end. There is also a small roll of paper tied over the inside end of the spolet with several strands of black match running through it. This provides a quick match type of effect and will give the shell a kick when it breaks. A shell using this extra step will break noticeably better than one without. Spolets are necessary for multi-break shells because time fuse burns for too long for proper timing between breaks. As you can see, the top shell has the spolet rammed with the most black powder, and between the other shells there is less black powder delay. This is because the first spolet must burn long enough for the shell to reach its proper height, whereas the second and third shell must burst faster because they are already at the desired height when ignited. Now, the only difference between a standard canister shell and one used for a multi-break shell on the exterior is where the protective discs are placed. In our original canister shell drawing, there are only protective discs on the bottom of the shell. On a multi-break shell, the very bottom break, the one that will be in direct contact with the lift, needs a protective disc on the top as well as the ones on the bottom. In this drawing you can see what I mean. The reason for this added top disc is to protect from the break of the shell above it. When I flip this page over, you can see in this drawing what it would look like all spiked together. You can see the next shell above also has a disc spiked to the top to protect from the shell one step higher, and so on. The very top shell needs no discs because it is not under threat of the lift, and it is the very first shell to burst, so it needs no protection from any other shell. Every shell break is pasted once the discs and spiking are finished, just as a typical single break shell would be. The only difference being that the shell must be spiked as if there were another fuse coming out of the bottom, so that later a hole can be made in that shell without badly damaging the spiking. The only thing left to explain now is how to attach all of the shells together. You may be wondering at this point how the fuse from the bottom shells are inserted into the shells above. The answer is as simple as it could be. Since there is no support disc on the bottom of the brakes except the very last, it is easy to use a drill bit spun between the fingers to puncture the layers of gum tape and the thin shell cap. Once done, the spolet on the shell to follow is inserted into the hole, and the two shells are pushed together. A bit of newspaper or tissue paper between the shells can help make a snug fit. None of the brake is let out to make room for the spolet to enter. Instead, it is further compressed by the insertion. The bottom shell and the second from the bottom must be the first to be joined. Then, to hold them in place, thin but very strong string is used to spike the two together in vertical wraps only. Before that is done, 1 or 2 layers of gum tape are wrapped around where the shells join to prevent fire from getting between them. The next shell up is joined and spiked once again, this time to both of the shells below it, and so on for every break afterwards. This is why thin string must be used, or the addition of spiking for every additional shell added will begin to build up on the overall width of the shell. When the very last shell is added and the final vertical spiking is complete, a long horizontal wrap is tightly spun around the shell until it reaches the bottom and is tied off. This wrap must be extremely tight and serves the purpose of further tightening all the previous vertical wraps as well as securing them into place. After this, the final layer of the shell consists of a few layers of paper, only covering the spiking, not pasted on to hold it in place, such as the final layer of gum tape does on each shell's individual spiking. The reason this layer is not pasted on is to allow the spiking holding on each shell to fall away once that shell breaks, so it does not interfere with the break of the shell below it. Outside of these final wraps of paper, the lift is added, the quick match is run up the side to the top spolet, and a quick match leader and delay fuse is added, and the shell is complete.
Alright, that wraps things up. As I said, this is not a video that a beginner is going to be able to walk away from and go build a multi-break shell, but if you learn these concepts, you will have a much better understanding of some of the most complex and beautiful fireworks in the world, which certainly will not hurt your designing abilities. I hope you enjoyed this video, despite it being a bit of a lecture, and if you took something away from it, be sure to leave me a comment. See you guys.